failed to drive you away, so we're going to wrap it up a little bit here. Good. Let me take, I don't know what the canonical time is, 35 minutes or something like that, and get into the next level of we're going on step by step. People have asked questions about the notes by Professor Prusen. I put them up there simply because those are the ones he used before. They're on B courses. They're a little bit stream of consciousness. Stan was not a person who was a hand holder. The notes may be a little more intelligible after seeing my slides, but I'm trying to make that my slides are self-contained in and of themselves, and they go up immediately after each lecture. So this was our toolkit from last time. In fact, not everything up there we did last time, but that's okay. One thing that will be useful, of course, is the definition of a kiloton, relationship between an electron, volt, and a joule. The two languages we talk about energy. We didn't talk about this quite yet. What a mole is, and then something the speed of light, in case you didn't know that, again in MKS units, 3 times 10 to the 8 meters per second. So today I just want to get you into the landscape of atoms and nuclei and relevant scales and familiarity with beginning to do some manipulation of calculation of energies, how to find masses, and so forth, and introduce you to the online, the Brookhaven National Nuclear Database chart of the nuclei, which is going to be great fun for you to meander about. I'm going to issue a homework that's going to have some real simple stuff on it, and I'll give you a flavor for some of what the problems are going to be. And again, the scientists and engineers can go down to the balls or just hang in here. Okay, interesting thing. How do we know the size of an atom? An atom is a neutral object, I think you know, we'll go over this a little more, with a nucleus in the middle and a cloud, a puffy cloud of electrons around it. Interestingly, the first, maybe not the first, but I think one of the first estimates for what the size of an atom was, or a molecule at least, was given to us by Benjamin Franklin, who did an interesting experiment. He took like a thimbleful of oil, mineral oil, he went to a pond, he dropped the oil on the pond, and the oil spread out into an oil slick, but at some point it stopped. And he said, oh, it's about half an acre. He said that's a teaspoonful, so you can estimate what a teaspoonful is. Pick a number, it might be a cubic centimeter or something like that. And good thing, I mean, the thing about doing science and technology is you have to become comfortable about making estimates, order of magnitude estimates. And he said that this thing stopped after it spread out to an area of half an acre. That's a very crude estimate. But if you take a teaspoonful and half an acre and put on your thinking cap, you can calculate the size of an atom. Think about what happens and why the thing spreads, and then why does it stop spreading. Anyway, this is what you'll come up with. Well, he was calculating a molecule, which is oil with some complicated hydrocarbon, 2 carbons, a bunch of hydrogen, and so forth. But you'll get a number that might be a factor of a few larger. This is, without going into a lot of whys and wherefores, what we know about the size of the relative size of things. Don't pay attention to everything here. Atoms are about 10 to the minus 8 centimeters. That's 10 to the minus 10 meters. Interestingly, almost independent, well, there's not a strong systematic dependence of the size of an atom on what the atom is. A lead atom is not terribly larger than a hydrogen atom, although it's got 82 electrons and a massive nucleus on the inside. Just out of curiosity, again, I'm asking the economists and political scientists and policy people, what's a wavelength of light, roughly? very crudely in size.
Visible light?
Yeah, visible light.
Like 400 to 800 nanometers?
Yes, which is about a micron, which is 10 to the minus 6. So light, just to give you a sense of scale, the wavelength is around 0.5 microns or 0.5 times 10 to the minus 6 meters. So we're talking about atoms being 4 orders of magnitude smaller than that, 10 to the minus 6 meters. Okay, now inside of that, and this is the remarkable thing, we have an atom is neutral by definition. Inside of that, we have an atomic nucleus. And well more than 100 years ago, when people started doing this business, the wizards of their time, they had the idea that an atom was neutral. You could pull electrons out of it. So they said, well, if there's electrons, negatives up there, there's going to be some positive in there. They came up with a crazy thing called a plum pudding model. In other words, it would be some kind of amorphous jelly. Electrons are in this kind of positive background. And the guy who is the father of nuclear physics was Ernest Rutherford, originally from New Zealand, did his research in the UK, was the one who made the astounding discovery that you got all these negative electrons. What made up the positive in the atom is a tiny little thing, very, 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 very tiny with respect to the atomic nucleus, that might be 10 to the minus 12 centimeters, so about a factor of 10,000 smaller. So let me put it to you this way. If the atomic nucleus was the size of a marble here, and you had this sort of puffy cloud of electrons, doesn't quite have a sharp edge. The size of the atom, the extent of the atom would be over around the Rothland Hall, where my liege lord sits, over there, a couple hundred meters away. So here's the size of the nucleus, and from here to the Rothland Hall is the whole atom where the rest of the electrons sit. Forget about those. Here's Ernest Rutherford, and he did these interesting experiments. Again, this is not anything you're accountable for, but it's very interesting. He took a source of a radioactive source that shot out alpha particles, which later on we'll find out are helium-4 nuclei, zipping in at 5 MeV per 5 MeV. And the plum pudding model said, well, this thing should be like jelly, it should just go right through. In fact, what he found was that some of these alpha particles actually came back at very wide angles. And his comment was, as if you fired a 15-inch naval shell at a piece of tissue paper and it came back. 15-inch artillery, projectile, and it bounced back. If you shot a bullet through watermelon, a field of watermelons, of course, the bullets would go right on through, and you get some flotsam jetsam going downstream. If you shot at something like a peach, occasionally one of the little beads or something would actually come back because it hit the pit on the inside. So he had actually found the pit of the atom, but it was very, very tiny. I won't go into a lot of details here. So let's get into some nomenclature. In fact, again, for our non-scientists and engineers, who can rattle off the first few atoms in the periodic table? What's the latest? Hydrogen. What's next?
Helium?
Helium.
No.
Lithium. Brilliant. Boron, carbon, nitrogen, oxygen, fluorine, and so forth. Okay, you've seen the chart of the elements. We're going to have our own chart, the chart of the nuclides. The nuclei are a little more complicated because, of course, you have what was discovered. This was an interesting thing. You have the nucleus is not just protons, except for the hydrogen. That's the only thing that has protons as the nucleus. It has protons and neutrons, which are essentially almost the same way. This was a mystery. In that you had these two things that we call generically nucleons. which is generically protons or neutrons. And if we say, what's the total number of nucleons in the nucleus, it's the sum of the protons in the nucleus. They're almost the same mass, except for a very, 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 very tiny difference. One of them is charged, one of them is neutral. Here's aluminum. That has atomic number 13, 13 protons. The mass number, which is always a perfect integer, is 27, which means to say there are how many neutrons?
14.
14. 27 minus 13. So the mass number is 47, and there's 13 protons, so there's 14 neutrons. So we write it like this, with the superscript in the upper left-hand corner. I guess maybe a little bit confusing if you've not seen this before. You write Z down here. However, you normally don't have to write that, because if you say aluminum, everyone says, it's 13. If it's calcium, it's 20. If it's boron, it's 5. So you don't have to write it, because if you know the symbol, you know what that is. Okay. Okay, so this is what to think about. Again, this gives no sense of the proper scale. Interesting thing about the chart of the nuclides is the atomic nuclei, you can have the same charge, i.e., when dressed with its electrons, it's the same chemical element, but different masses. Even right at the get-go, right out of the gate, your lightest element, hydrogen, has 3 isotopes. You have ordinary hydrogen, you have deuterium, which is hydrogen, or which is a proton plus a neutron, and in tritium, proton and 2 neutrons. Both of these are hugely important to nuclear power and nuclear weapons in the history that you're going to hear about from Professor Knott. There's more cheesy graphics. Lithium, you have lithium-6, lithium-7, both stable, lithium-8, unstable beta decay will come on later on. So this one has 3 protons, 3 neutrons, 3 protons, 4 neutrons, 3 protons, 5 neutrons. Not more, well, you can find some more, but we'll come into this a little bit later. We say that something, it has to say it's the same element. By that we mean that essentially the chemistry is the same, because what determines the chemistry, how things bind together, et cetera, whether you can make it into a food, whether it will kill you, whether you can make a synthetic fabric out of it, whether it's a metal or not, is determined by the electron cloud out here and how these atoms bind together with their electrons. Now, the number of electrons is determined by the number of protons, because an atom is neutral. Okay, so what do we know about the nucleus? And again, this goes back to the time of Rutherford. It's very small. It has a reasonably sharp edge. People now have done these experiments that measure with exquisite detail the density of charge. It has a shoulder, but for all practical purposes, you can treat it like a square box type function. So this is the nuclear radius in a unit Fermis, named after Enrico Fermi, which is 10 to the minus 15 meters, or 10 to the minus 13 centimeters, like that. Not terribly important for you to know, but systematically, heavier nuclei are larger in a much more systematic way than is the behavior of the atomic cloud. And it goes like the 1/3 power of the mass number. That tells you something. That tells you that the density is about constant. So you can make much bigger nuclei, but in fact, the radius grows very slowly. If I put it to you this way, make a very simple comparison. If I take 27 ping pong balls, which is 3 cubed, 3 by 3 by 3, glue them together, that's mass 27 ping pong balls, but the edge is 3. If I do 64 ping pong balls, 4 by 4 by 4, you've more than doubled the mass of the thing, but the edge has only gone from 3 to 4. That's because they, quote unquote, close pack. Nuclei are not quite that simple, but that's sort of what's going on. Interestingly, you can't find any crazy isotope you want. You could say, give me a nucleus that's boron but has 38 neutrons. It doesn't exist. Or give me a boron that has 5 protons and no neutrons. That doesn't exist. We'll get into this. Roughly, the charge, the Z is roughly M for the light nuclei. As you get heavier, you actually find that nuclei tend to be neutron rich for reasons you can guess. Why might nuclei be neutron rich as you get heavier? Again, for my non-scientists here. And not a big deal if you can't guess it right now. There's associated energy of the fact that the protons are charged. Okay, it's a little bit unnatural to. Okay, now the Coulomb, the electric charge is a weaker, much weaker force than nuclear force. Nuclear force is very, very, very strong, and it's short range. So nuclei more than about a Fermi apart at their surfaces typically will not interact. So it's very strong close in. When you're more than a Fermi away, the interaction is very, very weak. Okay. All right, let's talk about masses here. I told you that last time we have one language called MKS, which is convenient for describing your weight, my weight, the watermelon, and so forth. It's very inconvenient to talk about elementary particles. But then I told you that we're going to have a new language, nuclear atomic language, where we measure things in their mass energy, mc squared, which is much more convenient to talk about, and you can keep these numbers in your head. Mass of an electron is 9.1 10 to the minus 31 kilograms. Like, what? So, okay, that's like 10 to the minus 30 kilograms. So it's like decimal point, 29 zeros and a 1. Like, who wants to keep that in your head? Okay. Mass of a proton, 1.67 10 to the minus 27. Neutron, 1.675. So they're very, very, very slightly different. Sort of like 1 part in 1,000 different. Neutrons slightly heavier. We define something here it's called typically U, or AMU, atomic mass unit, which is 1/12 of the mass of a carbon atom. Not a carbon nucleus, they're carbon atoms. I didn't do this, but okay. So it's the carbon fully dressed with its electrons. So it's 6 protons, 6 neutrons, and 6 electrons. If I take that mass and divide the mass by 12, interestingly, you might say, well, forget the electrons. Electrons are kind of trivial. You might say, well, since it's 6 of this, 6 of that, it should come out to be the average between a proton and a neutron. No, it's actually significantly lighter than both. Gets back into the thing, we'll repeat it a few times, it gets back into the thing we talked about last time about the scale. You know, is a bound object heavier or lighter, according to Albert Einstein? So it's very, very, very slightly small, by about, again, 8 parts in 2,000. As I mentioned, the proton and neutron are about the same mass. Note the proton and the neutron each are roughly 2,000 times, actually 1836, heavier than the electrons. So electrons are very, very light. Most of the time we will ignore them. Here, we did this before, but now we're summarizing it again. In terms of the mass of the proton, it's 938.27. The neutron is 939.565. And the electron is half an MeV. So there's a factor of almost 2,000 between those guys. All right, and the AMU is 931.494. So in fact, you see it's a full 8 MeV lighter. So 8 parts per thousand, roughly, lighter. The binding of the carbon, and even including the electrons, make it about 8 parts per thousand lighter than the sum of the constituents. And I'll have you do a problem on this. I'm going to give you a very simple problem on the homework to show you not to be afraid of my homeworks. Suppose I told you, I'll make you do this calculation, that the mass of the proton is 1.673 10 to the minus 27 kilograms. On the next page, I tell you it's 938.272. In two separate steps, how do you go from kilograms to the MC squared expressed in EV? What's the first step? And again, just asking my economist input of time and so forth. MKS means if I calculate consistently, if I use units in kilograms, meters, and seconds, I will get energy answers in joules. Now, did I tell you how to go from joules to EV? Last time. Okay, so on one very simple homework problem, I'm going to have you go from the kilogram expression of the proton to the MeV expression for a proton. You would say, ah, you discovered the world. All right, so let me talk about 4 different ways that you see mass expressed, or 3, but it's actually quite simple. Whoever, some international union of pure and applied physics, whatever, sort of said, okay, we'll define, by definition, one atomic mass unit to be 1/12 of the mass of a proton, of the mass of a carbon atom, i.e. with the electrons, which are not entirely negligible, but I mean, technically, like that. Definition, 3 triple equal sign. On the main, all atoms are going to be, if you express them that a nucleus that has, or an atom that has 93, a mass unit of 93, you would say should be roughly 93 AMU. But since the binding might be a little bit different, it might be a little bit up, might be a little bit down, but generically, the baseline is to say that, you know, a nucleus or an atom that is mass 64 should be roughly 64 AMU, but it might be a little bit different from that. And so one way of expressing the masses is simply to express it in terms of the atomic weight, not the atomic mass, which is the weight relative to this. We'll get into that in just a second. Another is to say to take the atomic mass. This is called the mass excess, and this is what you see on the table. I'm going to show you and you're going to play with from the Brookhaven database. Is simply the mass here minus the pure integer A. If everything had the same average binding as a carbon atom, that would come out to be 0. And then since this is a mass, if I multiply by c squared, I get a number in MeV. We'll come back to this in just a second. So let me show you, when you look at various tables, you may see typically 2 common ways. Typically the mass expressed in AMU and also the mass excess. And let me give you a very simple analogy. And once you see the analogy, you will discover the world will be very simple. Let's just say that the International Union of Pure and Applied Physics describes an HMU, which means a human mass unit. And a human mass unit is 165 pounds. Okay, now, I weigh, despite all my good efforts and abstemious dietary habits, 175 pounds. A trim athletic student over there weighs 155 pounds. So this is Carl, and here's Bob. Okay. Now, in the calculation of energy release I wasn't pointing. You're much even better than that. And energy release is all going to be associated with the difference of mass of an initial system, a final system, the nucleus breaking into 2 or a reaction occurring or something like that. So the energy release is going to be differences at the beginning, the initial and final. So we're going to be talking about differences. If you want to calculate the energy difference, I simply subtract it. Another homework problem I'm going to give you is to convert 175 pounds into MEV. In other words, the mc squared me, which is a terrifically large number. So that's one way of calculating. This is just the mass itself. The way to think about the AMU is to say, in terms of the AMU, the facetious AMU, is to say, well, if an average human being is, or a presumably average human being is 165 pounds, I am actually 1.061 HMU, and Bob is 0.939 HMU. And if I say, now go calculate for me the actual energy release or whatever, I want the energy, give me the mass difference, you subtract this number from that and multiply by 165, and you get 20. The third way, think about the delta, the mass excess, is simply the difference above or below that. So in my case, my mass excess is plus 10, and Bob is minus 10. And again, the difference is going to be 10 pounds. So you calculate, no matter what you're talking about, in some tables you'll see the mass excess, sometimes you'll see the atomic mass unit. It's all, you can calculate consistency. It's all the same. You also do see, by the way, the binding energy. We talked about this. If I take 4 separated, 2 neutrons and 2 protons, all separated, and by whatever number of reactions I want, form them into an alpha particle, remarkably, the alpha particle, or the nucleus, excuse me, is lighter than the 4 neutrons. So I take the sum of the initial parts, the mass of the 2 neutrons, 2 protons, subtract the final state, and that gives you the potential, the energy. This is what you, going from potential energy to kinetic energy. This is how you get energy release. Oh, and by the way, physicists, particle physicists, talk about MEVs, and in fact, they imply that the c squared is there. You know, but it's, the mass is, it's really the mc squared, not that, but that's how we talk. Okay, here is some nuclei, or atomic masses, sorry, this is with the electrons, but, okay. Here's 12, carbon 12, and by definition it's 12.000 because it's defined to be that. Note that, for example, lighter things are the integer plus a little bit, which means that their binding is not quite as great. Their binding energy is not quite as great as per nucleon as the carbon. All of a sudden, you get up in the middle range, and all of a sudden you find that, for example, these mass 22 is 21.99. So it's lighter, which means it's more strongly bound on the average than carbon. Unfortunately, they don't show up to iron, which is the tightest. But here's mass potassium 39 is 38.96. So in fact, it is also more tightly bound because it's lighter than the, more tightly bound on the average than the carbon nucleus. And then uranium, actually, uranium-235 is actually, again, 235 plus 0.0439. So it's less bound per, and this is very important. We'll come back to this in a second. Okay, now let me play with this chart here. And you'll need this to do your homework. I just want you to have fun with this. This is a fun thing to peruse here. What I want you to do, by the way, let me just, well, let's look at this and look at the next slide. So here's the thing I said before. Everything in black, by the way, is a stable nucleus. It lives forever. Then you see colorations I'm colorblind. You see some bluish and some reddish and yellowish and so forth. Those are things which are short-lived, i.e. you can make the nucleus, but it doesn't live forever. One way or another, something happens to it, it decays. But you see, you can't find crazy things. I can't find Z of 20, that's calcium. I can't find calcium. I can find calcium 48. I can even find calcium 52. I can't find calcium 190. I can't find something that is, for example, tin 50 or 72. So all the nuclei are confined to this thing here, which is like a long valley. In fact, that is exactly what I want you to think about. So let's actually, what I want you to do is you're going to, whoops, I have to put arrows. Come on, baby. There we go. Okay. Yeah. Here we go. Come back here. So I'm going to click on this link. Yes, and now I'm at Brookhaven. So I take my cursor. Let's look at mass 28. Let's look at silicon 28. Nice, interesting nucleus. So much of the Earth's crust is made of silicon 28. Well, let's do the following thing. We'll go to aluminum 28. We'll go to zoom. Okay. Click. All right. So the only thing I want you to play with, and I'm going to have you do a few exercises where you just have to kind of rummage through the chart of nuclides, is here's the mass excess. So it's minus 16.9 MeV. So its binding is stronger per nucleon than a carbon-12 nucleus. If it were exactly the same binding per nucleon as carbon-12 nucleus, delta would be 0. Now here's something interesting. Let's go to mass 29 just to make this a little bit easier. Here's aluminum 29. Aluminum 29. Notice the binding here, or the mass excess, is minus 18 MeV. If I go to silicon 29, it's minus 21. If I go to phosphorus 29, it's minus 16. Sulfur 29, it's minus 3. It's getting more and more weakly. If I go on this side, magnesium 29, minus 10. Sodium 29, it's 2 MeV plus. So what happens is that's the valley, it's the most tightly bound nucleon. If I go up, I get walls like this. So what you should think about is called valley of stability. And you should think about this like Yosemite. Let me get out of this thing here. It is indeed a valley. If you go through hiking in a valley, you get something like a parabolic or shape like that. When you go through the chart of nuclei, the black line, the nuclei are stable because when you get off there, all of a sudden their masses, they become kind of unnaturally light. And they will actually find a way, as I was in physics, of decaying down. So actually, let me just show you a couple of things. We'll make this quick. Let me show you this. This is mass 140. Praseodymium 59, neodymium 141, neodymium 141, which has got a Z of 60, is heavier by roughly an MeV. Another MeV, and so forth. This one doesn't look parabolic, it looks a little bit more linear. But you see, the valley of stability is here, and then the walls up there. And at some point, it gets to the point where these things are not bound at all. And that's why the chart of nuclei stops. Now, here's the money slide. And after this, I can turn the floor over to Professor Knopf. Everything about this course is on this slide. This is where nuclear energy comes from. For any nucleus, I take the sum of the parts, all separated, weigh them. I put them together in a nucleus, I weigh them, mc squared, and then I divide by that, what's called the total binding energy by the nucleon number. On the average, well, it gets up to about 8 MeV. What you see is that for very light nuclei, the binding per nucleon is low, 2, 3, 4, something like that. Iron, in the region of iron, is the most tightly bound nuclei in the chart of the nucleus. Very heavy things are well bound, but not as tightly bound. So let's do a simple experiment. Let's look at uranium-236, which is a neutron that drifts into uranium-235, and bang, you get fission. The binding energy here is about 7.5 MeV per nucleon. So A of 236, the binding energy per mass unit is around 7.5 MeV. What happens if I take that nucleus and I take it apart into 2 equal pieces? Actually, it tends to go into asymmetric ways, but just for now. 236 divided in half is 118. What's the average binding energy of a mass 118 nucleus per mass unit? What's that? Estimated roughly off the graph. Just eyeball. 8. A little bit more. It's around 8.5. Not quite 8.5, maybe 8.4. This is for 236. Now for 118, it's around 8.4. So you see, if I now calculate the difference in energy, the final state to the initial state, it's 2 of these with 8.4. This is 238, 236 times 7.5. Now, 2 times 118 is 236. So basically, the difference is slightly less than an MeV times 236. This is the difference. That comes out to be a number on the order of about 200-something MeV. That's the energy release per event of fission. That is a huge energy that's locked up in the nucleus and then comes apart. And the fact that this curve goes up, peaks, and comes down gives you 2 ways of getting energy out. One was like falling off the log. The discovery of fission in December of 38 to the first reactor in 1942, which is 39. And then from there to a bomb within 4 years and reactors and electricity, just like falling off the log, is breaking heavier things to lighter things, which are more tightly bound. And then this thing has been a fool's errand for getting on a century now, which is fusing lighter things. In principle, there's a lot of energy here, but this has just been hellishly hard to do. So going lighter things, which are less lightly bound, to heavier things, which are more tightly bound. By the way, but that does play into thermonuclear weapons. And I'm going to turn this over just to say that unlike the energy in if I take a rock, I can heat it up continuously and get any energy in the rock I want. When you look at atoms and nuclei, there are finite energy levels. This has to do with quantum mechanics. It'll be important to you later on. You don't need to know anything about that. But just to say you can't have a continuous degree of excitation in atoms. In the case of atoms, the differences are all measured in EV. Excitation levels in, for example, the ground state of carbon compared to the first excited state is 4.4 MeV. Again, the currency is off by a factor of 1 million. And there's your toolkit for lecture 2. I'm going to give you some very easy problems, and you will establish a lot of confidence by just doing some simple 4-function calculator problems.